Hi students, in this video we are going to discuss about the linear phase realization. For linear phase realization, what we need to do is we are going to incorporate the condition h of n is equal to h of n minus 1 minus n, and we know the transfer function of the filter is h of z is equal to summation n is equal to 0 to n minus 1 h of n z power minus 1 minus n. Okay, now here what we are going to do is we are going to consider the two case n is equal to even and n is equal to odd. Here h of z is equal to, for if this n is even, I am going to split into two half. Okay, so here 0 to total length is n minus 1, so I am going to split as center is n by 2, previous sample is n by 2 minus 1, so you will get n minus 2 by 2. That's what I have written here. Okay, so I have divided the even samples. Even, suppose n is equal to 8, so substitute n is equal to 8 here. So what you will have is n is equal to 0 to 8 minus 2 is 6, 6 by 2 it is 3, so summation 3 plus here n is equal to 8, so 8 by 2 is 4, so 8 minus 1 is 7, so 0 to 3 and 4 to 7 I have splitted into two sequences. So here totally is 0 1 2 3 4 samples, here 4 5 6 7, totally 4 samples I have splitted into two equal group. Okay, now what we will do in linear phase realization, one half is equivalent to another half, so I am substituting h of n is equal to h of n minus 1 minus n. So and also I am changing this summation when I substituting this replacing when I use this equation, linear phase symmetric equation, so I am going to replace n is equal to 0 to n minus 2 by 2 h of n minus 1 minus n. So wherever you are having n, there I am going to replace n minus 1 minus n. So this here also I am replacing this, and also we know that h of n minus 1 minus n is equal to h of n. I think already we have discussed in this FIR filters at the starting concepts. Okay, so summation n is equal to 0 to n minus 2 by 2 h of n z power minus n, summation n is equal to 0 to n minus 2 by 2 h of n z power minus n minus 1 minus n. Okay, so taking h of n, so you will have this relation. Okay, so this is what your h of z. Now I need to realize this, since it is an even, so how will you perform the direct form realization? First you will draw the number of delays, right? Similarly here you need to draw the number of delays considered. Here I am having some so I don't know how much the value of n, so I am drawing the delay. Since it is even, you will have an equal half here, so here z inverse. Okay, so here I have drawn the delays, where the delays here is nothing but n minus here the summation varies from n is equal to n minus 1 by 2, right? Here it is n by 2 minus 1. So here totally this n takes the values of 0 to n by 2 minus 1, so that much of delay you will have. So here what we need to do is the input is x of n, right? So what are all the values you will get, it will added. So here when you substitute n is equal to 0, you will get h of 0, then z power minus 0 plus z power minus n minus 1. Yes, this is what the thing you will get it. So z power 0 is 1, so you will get h of 0 1 plus z power minus n minus 1. So here how the last delay, so here you will have n minus 1 delay, so this is the last delay. So before performing delay, so this and this will be get added. Okay, so the resultant output you need to take it. Okay, this is multiplied by h of 0. Understood? So this is multiplied, that is 1 without delay. I am taking the input sequence plus z inverse n minus 1 last delay. This is n minus 1 delay. So I am adding it according to this equation, then multiplying by h of 0. Okay, so plus, then when you substitute n is equal to 1, what you will get? I will get h of 1 into z power minus 1, z power minus n minus 1 minus 1. that is previous delay of n minus 1 minus 1, this one. Okay, so here this is what here I will get it z inverse. So previous delay of z is n minus 1 is this one, so it is added. So this is, so here put like this, here this is multiplied by a coefficient h of n. Okay, so similarly here, sorry, here two delays are added, multiplied by a coefficient h of 0, like that it will proceed. Okay, so here this is what your center one, so this is multiplied by this output. Now we will get h of n, so here n minus 2 by 2. Okay, so now you need to perform an addition operation of these things. Okay, so finally you will get a resultant like this. Okay, so this is what your output y of n. Okay, so here this is for n is equal to even case. Similarly we are going to draw for n is equal to odd case. Now the same delays I have drawn, so similar to this, here if you want you can draw a delay like this. So here I have drawn a delay like this. So what you need to do first, here n minus 1 by 2 z power minus n minus 1 by 2. Okay, so consider this is n minus 1 by 2 delay. Okay, this portion is n minus 1 by 2 delay. So what I am going to do is I am going to multiply this with h of n minus 1 by 2. First I will complete this. Okay, then here this is what your input x of n. Okay, so first when I substitute n is equal to 0, what I will get, I will get this x of n plus this value, it's going to add and it's going to multiply with h of 0. Okay, next similarly here this value and this value I am going to multiply with h of n, then this value I am going to multiply with h of 2. So similarly this will proceed, so this value adder and this value, then I am going to multiply with h of, so this is what n minus 1, right? So previous of n minus 1, that is n minus 1 by n minus n, sorry, n minus 1 by 2 minus 1. So previous value is n minus 2 by 2, so n minus 3 by 2. So this value is now n minus 3 by 2 output. Okay, so here now you will get n minus 3 by 2. So finally you need to add it all the things. Okay, this one, finally you need to add this with this, so you will get the output y of n. So this is what your linear phase realization for n is equal to odd and n is equal to even cases we have discussed. We will see problem related to this. Now consider this problem. Here they have given transfer function. We need to perform the linear phase realization. So the first case is what we need to do is we need to expand this. So after multiplying this you will get this answer. So now consider how many delay elements are there. Okay, here the order n is equal to 5. So here you will have, when you have summation you will have n minus 1. So here 4. Okay, so here therefore n is equal to 5. So how many delay elements are there? There are 4 delay elements. You draw in this manner like this, because you are having only 4 delay elements, so draw like this. Okay, whether you understand now, if n is that is odd, you will have even delays. Okay, so like that, if n is equal to 4, you will have n is equal to 3, that is odd delays. Okay, so I am drawing like this manner. Okay, so here what we need to do is, first this is what your input x of n. So this x of n and this the last delay coefficient I am going to it is same, right? So here I am going to consider this as 1, then this delay, right? this one plus this coefficient z in 3 minus 3, 1 2 3, third 3 delays, right, are same, which is 3 by 4. Then this coefficient, that is here the output of second delay is multiplied by 17 by 8. Okay, so the finally what we need to do, we need to perform an adder and you will obtain the output y of n. So this is what the linear phase realization. And the another thing is, you normally you will perform cascade realization, right? So here using linear phase also you can perform cascade realization. Now see in how will you perform is, in order to perform cascade realization what we need, you need uh, you need factors, that is more than one, right? So here I am having two more than one factor, so I am considering this. So now perform this separately linear phase realization. Now consider this case, how many delays are there? You are having two delays, right? So you draw like this. Okay, so what will be the, how will you add this? So here this one and this coefficients are the same, so z power 0 and z power minus 2, that is the input without delay and the input after passing two delays, the coefficients are same, that is 1. Okay, so I am drawing one like this. So here the next one is 1 by 2 z inverse. Here I am taking the output and I am multiplying with 1 by 2. So finally I am going to add these two. So this is what the output of the first one. So this is what fed as an input to the next. Okay, so now here also consider how many delays you are having. You are having two delays, right? So what you need to do, the same concept you are going to do. First, this is what the input, I am going to take the output, just both the coefficients are same, so here I am going to perform an adder. So here it is going to multiply by 1, then here this is multiplied by 4, then it is going to add using an adder. So this is what your output y of n. So like that you can also perform cascade realization using linear phase realization. Okay, so now we have come to the end of this topic, that is the unit 2 FIR filters. So here we need to know the advantage of linear phase filter. Suppose if we realize this structure, okay, using a direct form 1. Okay, so how many multipliers you required? You required 1, 2, 3, 4 multipliers you required. Okay, now see when you realize using a linear phase structure, so here you need one multiplier, you need another multiplier, here also you need another multiplier. So how many multipliers you need? You need 3 multipliers, that is the number of multipliers is reduced. Okay, so this is what the advantage of an linear phase realization structure. So for here we can find out the number of multipliers when n is odd. Okay, when n is odd it required n plus 1 by 2 multipliers. So the here n is 5, so 5 plus 1 6, 6 by 2 3, so you got 6, that is 3 multipliers. For even case, suppose n is even, the number of multipliers required is n by 2. Okay, so this is what the linear phase realization. Thus we have reduced the hardware component here by applying the symmetric condition. So while implementing in a hardware, the number of multipliers will get reduced. Okay, so this is what the advantage of the linear phase realization structure.